Now that we know the definition of injective and surjective functions, we're going to look at injections and surjections for functions that are defined by formulas. So we're going to first review the thrower-catcher model for functions. We're going to review what the definitions are of injective and surjective functions. We're going to do an example of showing that a function given by a particular formula is injective, and then we're going to do another example that is surjective. So this is the same thrower-catcher model that we looked at before. In this one, a function is thought of as a coach who has a group of throwers and catchers. Each thrower has one ball. The coach tells each thrower, which, by the way, corresponds to the inputs of our function, to which catcher, which corresponds to the output, to throw the ball to. So the thrower, the input, throws the ball to the catcher, which is the output. And the set of throwers are the domain, and the set of catchers are the codomain. And just note, even though we call them catchers, that doesn't mean that they're thrown a ball, that they actually catch a ball. They are just ready to catch a ball in case someone throws it to them. So here is a reminder about what injective and surjective functions look like. Injective means that no two inputs have the same output. And surjective means that every element of the codomain is an output of the function. In other words, every element in the codomain has some input where that element is an output. Here is what injective and surjective functions look like with the thrower-catcher model. So remember, injective means that you can't have two inputs that have the same output. The inputs are the throwers, the outputs are the catchers, so that means no catcher gets thrown more than one ball. And then surjective means that every element of the codomain is an output. Remember, the outputs are the catchers who get thrown balls, so that means every catcher gets thrown at least one ball, maybe more if it has a lot of throwers throwing a ball at the catcher. So now let's look at a particular function. We're going to call it f. The domain is z, and the codomain is also z, the set of integers. And the formula is given by f of x equals x plus 2. So let's see if we can show if it's injective or surjective or both. So let's start with injective. So before we try to prove affirmatively that it is injective, we might want to look first what it means for f not to be injective. So here we're sort of angling towards a proof by contradiction. So we're going to assume that f is not injective, see what that implies, and see if we can get a contradiction. So what that would mean is you have two throwers, that's the inputs, that throwing to the same catcher, which is the output. So let's pretend for a while that f is not injective, so we're doing a proof by contradiction. And we're going to pretend that x1 and x2 are the throwers that throw to the same catcher. So x1 and x2 are the throwers, and then y is the catcher for both throwers. So that means x1 is the thrower, y is the catcher, so f of x1 equals y. x2 is a thrower, and y is also a catcher for that person, and so that means f of x2 is equal to y. And notice that f of x1 and f of x2 are both equal to y, which means they are equal to each other. So f of x1 equals f of x2. Note that f of x1, by definition of the function, right, f of x is x plus 2, so f of x1 is x1 plus 2. Similarly, f of x2 is x2 plus 2. Since they're equal, that means x1 plus 2 is equal to x2 plus 2. But now we can subtract 2 from each side of that equation, and we get x1 is equal to x2. And that is a problem, or at least a contradiction. It's not a problem for us. It's a problem for Peeves, because this contradicts the assumption that x1 and x2 were different inputs. We were assuming they were different inputs because we were assuming that f was not injective. That means that's a contradiction, and so f is injective. Now, there is one other way of looking at proving that it's injective or surjective. And it's going to end up with the same looking proof, but looked at it from a different point of view. So remember again that not injective means there exist inputs x1 and x2 such that x1 is not equal to x2 and f of x1 is equal to f of x2. And one thing that you might notice if you look carefully enough at that statement is it's a there exists statement. So if we want to find injective, we want to find the negation of not injective. Since not injective is a there exists statement, we've had experience finding negations of there exist statements. All right, so we're going to find the negation of non-injective. So what's that going to be? Well, remember, the there exists turns into for all. So instead of there exist inputs x1 and x2, it's going to be for all inputs x1 and x2. And then, where after the such that, we're going to negate that statement. So we're going to negate x1 not equal to x2 and f of x1 equals x2. And when we do that, we're going to have to do a couple things. First of all, it's going to be an or statement. We're going to use De Morgan's law. And we're also going to negate both of the individual statements. So x1 not equal to x2 becomes x1 equals x2. And then f of x1 equals f of x2 becomes f of x1 not equal to f of x2. So for all inputs x1 and x2, either x1 is equal to x2 or f of x1 is not equal to f of x2. Now let's look at that second part, that or statement, because that actually looks like one of the logical equivalencies we did way back in chapter 2. And if you forget it, I forgive you. You should go back and look it up just to make sure I'm not lying to you. But remember, in the old days, we had the logical equivalence Q or not P is logically equivalent to P implies Q. That was one of the things that was equivalent to P implies Q. Remember, you had three of them. One was P implies Q, the other one was not Q implies not P, and then the third one was Q or not P. So in this case, our P is going to be f of x1 equals x2. Our Q is going to be x1 equals x2. So when we replace that, right, we're going to have a function being injective being logically equivalent to for all inputs x1 and x2. Now let's see. So the P is f of 1 equals f of x2. So it's going to be if f of x1 equals x2. Right, because the not P is then going to be f of x1 is not equal to f of x2. And then the or Q is going to be x1 equals x2, so that then x1 equals x2. And if you're looking carefully at that, that's pretty much what we proved in the previous slide. But let's see how it works in this one. So we're going to assume that f of x1 is equal to f of x2. We're going to show, in other words, x1 plus 2 is equal to x2 plus 2. And then we're going to show that x1 equals x2. So we have x1 plus x2 equals x2 plus x plus 2. We're going to subtract 2 from both sides to get x1 equals x2, and that was what we're trying to show. That means, that means that f is injective. Right? And again, if you look at this proof, and if you look at the one we did previously, the mechanics are basically the same. All right, so let's do surjective now. Now, surjective means that everyone in the codomain is a catcher, right? So does every element in the codomain, and in the codomain is a set of integers, get thrown a ball? So does every integer get thrown a ball? So we have integers throwing the ball, that's our domain. We have integers also catching the ball, that's our codomain. Well, let's see. So let's suppose we have some random y in the codomain, so that means y is an integer, right? Because that's what the codomain is. How can we tell whether or not y catches anything? That's a good question. Well, there's more than one strategy generally, but the most reliable strategy to look at first is figure out who's going to throw the ball to y. Because if you find out which integer throws the ball to y, then that's going to be your input, y is going to be your output, you're done, right? So we got to find it, right? We got to do some work. So let x be the thrower. That means we want x to be the thrower and y to be the catcher. That means we want f of x equals y. So I have f of x equals y not as something that I've proven, but something that I aspire to. That's what I want to prove, okay? So I want f of x to be equal to y. So, and I want to know which x is going to do that. Well, if I had such an x, remember f of x is x plus 2, where x is the input. And if I put those two together, that means y has to equal x plus 2. Now remember, my goal is to find out who's throwing the ball to y, so I'm looking for x. So I want to solve for x in that equation. I get x equals y minus 2. So my guess, I haven't proven anything yet, right? Right now I'm just sort of trying to figure out who the thrower is so I can test it to see if they actually throw the ball to y. And my guess is that the thrower in this case is going to be y minus 2, because that's what happened when I solved for x. So what we think we need, I said so we need, I'm feeling very confident, I suppose. What we think we need y minus 2 to be the input to get y as an output. But in order to verify that, we've actually got to plug it into the function to see if it works. So first of all, is y minus 2 an appropriate input? Is that something that I'm allowed to put in my function? Well, remember, in order to be an input, the domain is the integers, y minus 2 has to be an integer. So how do we know y minus 2 is an integer? Well, we know y is an integer. It's in the codomain. Remember, the codomain is the set of integers as well, so y is going to be an integer. That means subtracting 2 from y is also going to be an integer. Not the same integer, but it's going to be an integer, which means we can put it into the function. So it's in the domain, so we're allowed to put it in the function. So we get f of y minus 2. Well, what does f do? It takes your input and adds 2 to that input. So it takes x and takes it to x plus 2. That means it's going to take y minus 2 and add 2 to it. And thankfully, the negative 2 and the positive 2 cancel, and you end up with y, which tells us if you put y minus 2 as an input, you get y as an output. Y is an output, and remember, y could have been any integer. So this is going to work for every single integer, which means that every integer is a catcher. So that means it's an output, which means that f is surjective. All right, so now I think you're ready to start proving some functions injective and surjective yourself. So there's one literally called that, proving functions injective and surjective. And then there's another one called cardinality, which sort of tells you how to tell whether two sets have the same size using injective and surjective functions. Those are on the PDF files included with this video.